We take another example. Determine whether the function f1 of x equal to x, f2 of x equal to x squared, f3 of x equal to 2x minus 3x are linearly independent. So we have set a function, and then as we have said, we take the linear combination, put that equal to 0, and we say if all the c's are not equal to 0, but this equal to 0, linear combination say linear. So we say take the linear combination c1 f1 plus c2 f2 plus c3 f3 is equal to 0. So get here c1x plus c2x squared plus c3 into 2x minus 3x squared is equal to 0. We open this one and get here c1x plus c2x to power 2 plus 2c3x minus 3c3x squared equal to 0. We compare the coefficient of both the sides. We take the coefficient of x. We get here c1. Here we get here plus 2c3. Right hand side is equal to 0, is equal to 0. This is my equation 1. Then I take x squared, the coefficient of x squared. That's equal to c2 minus 3c3 is equal to 0. This is my second equation. Now we solve these two equations and we try to find the value of c1, c2, c3. There are two equations, three unknowns, so there will be many solutions. Let us see. We take here our c1. c1 is equal to 2c3. What's my c2? My c2 is equal to, here is minus sign, and c2 is equal to 3c3. And then we say let our c3 is equal to 1. What's my c2? c1 will be equal to minus 2 and c2 will be equal to 3. So it means that if we write here over this, put the value of c1, c2, c3 here, so what we'll get? We get here this c1 is minus 2x, then here c2x squared, c2 is 3 plus 3x squared, then c3 is equal to 1, c3 is equal to 1 plus 2x minus 3x squared equal to 0. We compare the right hand side and left hand side and we see the result. Here is minus 2x and here is 2x, there are 0, where minus 3x squared is 0, so this is equal to 0, and this means the function that we say this implies f1, f2 and f3 are linearly dependent. So that's the way we can find the linearly independent. If we are able to find the c's are all zeros, that's equal to the linearly dependent. We have another way of looking on this linearly dependent and linearly independent functions. We're having one formula, we call it a Wronskian. Wronskian is a determinant. For example, I have the function, it can be more than one function, f1, f2. I take three functions and I try to find the Wronskian. Wronskian is a determinant. So get here f1, f2, f3, get here f1 dash, f2 dash, f3 dash, f1 double dash, f2 double dash, f3 double dash. We'll find the determinant of this one. If the Wronskian of the function f1, f2, f3 is not equal to 0 on I, then we say these functions f1, f2, f3 are linearly independent on I. We take as a note, this is only for linearly independent. It's not for linearly dependent. If this becomes 0, we have to check to prove the functions to be linearly dependent. We take our old definition that we have c1, f1, c2, f2, c3, f3 equal to 0 not all C's are 0. So that's, you have to note this one. This is only for the case that we are having linearly independent, not linearly dependent, and that's the new definition. We take a Wronskian of the functions, and Wronskian of the function is the determinant f1, f2, f3, then first derivative and second derivative, then calculate the determinant and check if it's not equal to 0, on the interval I, then we say that they are linearly independent. If this is 0, then we go to the old definition to prove that they are linearly dependent. So that's the thing you have to note. I explained you this with the help of example. We apply this Wronskian only when these f1, f2, f3 are the solution of the differential equation. This is not for the function. For the function, we use the old one, that we take the linear combination equal to 0. That's why for the linearly dependent, we take this one. For linearly independent, if f1, f2, f3 are the solution of the differential equation, then we calculate the Wronskian to check that they are linearly independent. So we have an example. We take that we want to find that the solution of the differential equation y double dash plus y equal to 0 are linearly independent. Solutions are the function f1 is equal to sine x and f2 is equal to cosine x. So it means we can use the Wronskian, because if they are only function, then we use the linear combination to check they are linearly independent or linearly dependent. And when it's the solution of differential equation, we can find the Wronskian. So solution of this one, we calculate the Wronskian of the function f1 is sine x and f2 is cosine x. That's our determinant. Here is f1 and here f2, f1 dash, f2 dash, and we can just write the determinant of this one. We get here minus sine square x minus cosine square x. We simplify this one, take minus out. We get here sine square x plus cosine square x, and this we get here, we know that this is sine square x plus cosine square x trigonometric identity is equal to 1. We use this one, we get here minus 1, which is not equal to 0 for any x in R. So that is for R real number. So say the function f1 of x is equal to sine x and f2 of x is equal to cosine x are linearly independent. And if they are linearly independent, then we can note here, we can write the general solution. So we can write here general solution of the differential equation. Because they are linearly independent, we can take combination. This is y equal to c1 sine x plus c2 cosine. You can write a linear combination of this one, and that's our solution. Again, before going further, this my equation was second order differential equation. We were having here two solutions, f1 and f2. Now if f1 and f2 were two solutions, and we calculate our Wronskian for this one, and we see this is our determinant f1, f2, f1 dash, f2 dash. Calculate, then we use the trigonometric identity. This cosine square sine square x plus cosine square x equal to 1. So get minus 1, and it's not equal to 0 for any real number. So we say when they are this one, then we say they are linearly independent. So we can say here that they form the fundamental set of solution. For fundamental set of solution, number 1, these are the solution of the differential equation. Number 2, they are linearly independent. Then we say they form fundamental set of solution, and we can write the general solution for that one, or superposition of the solution.